We're going to see how well Dropbox and OneDrive play together. Because now that I have the Galaxy phone, which I lost, so I think it's in my office. I had it 20 minutes ago. It is what it is, right? Huh? I think Samsung has a similar whatever. I'm 99% positive it's to sit in my office. Yeah, so we'll see how the two of them play, because you forget how reliant you are on things like iCloud. Because I do a lot of productivity stuff on my phone, like spreadsheets and things. Like I run my whole business off my phone. So whenever I all my invoices and stuff like that all come in and out of the phone. Well, so I keep a spreadsheet that has all checks and balances and stuff. Well, that's on iCloud. So I can't just open up Pages on the phone. I have to use Excel now, and Excel can talk to OneDrive. So now I need to get so I have written a piece of software that syncs certain folders between the two of them. All right, so let's look at this. What was the 210, 219? Yeah. Okay, 210. Add to the environment interface a constructor called extend env star and implement it using the A-list implementation or representation, whatever. The constructor takes a list of variables and a list of values of the same length and an environment. Okay, and does it, when it extends the environment, does it, okay, it's a third kind of constructor, right? We have an empty env, we have an extend env, which extends an environment by one variable value pair, and then we have an extend env star, which extends an environment by a list of name value, or a list of values, and or a list of variables and a list of values. Is that correct, or is it supposed to output extend envs? They give us an example. Yeah, looks like it can stand on its own, right? So it should be pretty simple. So this is extend env star to be a lambda that takes in a list of vars and a list of vals and an environment, and it creates a list containing extend env star, low vars, low vals, and env, something like that. Now, did they say we had to update apply env for this dude? So I guess there's two ways we can handle this. I would say based on the wording there, this was probably enough to meet the requirements of the assignment. I think that's a little weak, but go ahead.
I did there's just two lists. Well, two lists extending two lists. That makes sense. Where it's environments that contain.
Yeah. So what you did is, instead of having this new type of environment, you processed your list of vars and your list of vals into a whole bunch of extend envs, right? We'll write that version too. I'm just kind of, based on the wording, this is probably acceptable. How many of you did it this way? One lazy person? That's okay. I think the wording supports you being able to do this way, but then the follow through, and I won't take off for this, but the follow through probably then should be adding an additional cond here to apply env for handling that new type of environment. Now, if you think about it, so let's write the other thing first, and then let's consider maybe why that sucks. Let's go that route. So we're going to use Corey's crappy implementation. which makes sense. But what he did is he said, look, I'm not going to create a new type of environment constructor. Instead, here's a function that is a kind of syntactic sugar for creating multiple extend envs for me, right? Okay, so what he did is for this guy, let's write it as a second one just so we can have both. We'll say extend env 2 star, something like that. All right, and this guy is going to take in our lambda low vars and low vals and env. And what it's going to do is it's going to process that list of extend env, or of low vars and low vals. The assumption is those guys are parallel arrays, right? They have there's the same number of variable names as there are variable values. I think we make that assumption that A equals 5, B equals 7, C equals 9, whatever it is. Okay? So we need to process through that, generating a whole bunch of extend envs. So ultimately, we're going to build upon this environment. So the result of extend env 2 star will be a massive list of extended envs, where each individual environment has only one name value pair. Okay, so we'll go ahead and practice this with our cond. All right, so if we're dealing with the empty list, we're done, right? So if we're dealing with the empty list, null low vars, or you could also say null low vals, because those guys should be equivalent in terms of length, then boil down to the empty list. That will finish our cons that we're going to be having here. Otherwise, we must have something in low vars and low vals. So what we're going to do is now you probably could call our constructor for extend env, passing it a var, a val, and an environment. Oops, sorry. So what we're going to go ahead and do is we're going to call extend this is probably kind of a crappy use for a cond, but whatever. Because we only have two conditions, right? If it's the empty list or it's not the empty list, whatever. So we'll have our else here. So we'll go ahead and call extend env 2 star. So the same function, we're making a recursive call to the function, passing it the cdr of low vars, passing it the cdr of low vals, and then passing in a new environment that is the result of calling extend env on the car low vals, low vars first, right? The car of low vals and the current environment. So that guy right there results in a brand new environment, which is the environment or current environment env extended by a single name value pair. And that's the new environment we'll pass into this next call to extend env 2 star, like that. And actually then with that in mind, rather than the empty list here, actually, is the empty list going to be okay? If we're done doing those things, then we just want to boil down to the environment. Yeah. Because we're not actually consing stuff. We're ultimately spitting out a newly constructed, newly expanded environment. So once I'm done hitting all my name value pairs, my final produced environment is the last guy I passed in, env here. Does that make sense? So I think that's probably a more reasonable definition of this one. I don't necessarily care which one you did, as long as you can kind of appreciate both of them. Questions about this? All right, so now I promised you a follow-up question. Why is this second implementation stupid? I actually think the first implementation is the better implementation. as far as programming languages go? Well, certainly this one. Oh, go ahead.
Because it's a lot more messy and harder to follow.
Well, but these two guys do produce different things. It's not like this guy have highlighted there and this guy actually produce identical outputs. They don't, right? One of them creates a new construct for an environment. Okay. The second one here uses existing constructs to kind of MacGyver a expanded environment, an extended environment. So the second one we might say is kind of a convenience function for working with our current constructors for our environment, where this first one up here, all right, that one lazy student did, had a lot of laundry. One lazy student did really creates a brand new constructor for an environment. Now, why is creating this brand new constructor for an environment probably actually the better idea? Go ahead. Yeah, I mean, if we're kind of evolving our language here, you know, we're doing this weird tiptoe thing toward. We're starting to see now. We're kind of peeking behind the curtains a little bit and realizing that some of the stuff we've been doing is actually related to language constructs. But now it's becoming a little bit more obvious since we're like calling things environments and stuff like that. But when we think about our modern programming languages that somebody else wrote, Java, C#, whatever, we can kind of define more than one variable inside the same scope, can't we? That's pretty common practice for us. Now, it would make sense for them to kind of create a data structure, maybe called a scope, name it whatever you want, but that would make sense, right? That has a collection of name value pairs in it, whether it's a dictionary or whatever. It would make less sense for us to say, okay, well, I'm inside this interface and I want to define this guy and I want to call upon this variable. Well, let's go find out if he's resolved. So I'll look here. If he's not resolved there, I'm looking inside the same scope, but at another level up to see if he's resolved. Another level up, another level up. So we have a scope is implemented as a whole bunch of nested lists. And that might be problematic. Can you give me an example other than performance where that could be problematic without maybe a pretty drastic workaround? What about variables defined in terms of other variables within the same scope? It would certainly be easier to work with that in a flat list where we say, look, we have, you know, A is equal to 5, B is equal to A. If we're in a flat list there, we can resolve that relatively easily, right? Kind of thinking about the idea, at some point we've talked about, I don't know if it was even in here or a previous class, but the idea of a two-pass compiler where, you know, in the early days of like C programs, you had to create a prototype of your functions at the top. And that's where header files came from, and you know where you have a separate file, and because the compiler had to hit your prototypes first, so that when you actually first called your functions, it didn't matter if they had been defined yet. You know, we're used to today as modern programmers that we kind of put main at the top, and then all the other functions below, and you know they can call each other. It doesn't really matter if a function was defined already or not, as long as it's defined inside the file somewhere. Well, that relies on a multi-pass compiler that's going through and reading in all your symbols, so it kind of knows what are the legal things you can spout. You know, what kind of functions can I call, so that when you actually call them, it can give you compile errors when you screw up. Make sense? So, having a environment constructor that gives us that more robust collection of name value pairs probably makes some sense. Right? And I'm sure that's why you implemented it that way. It's absolutely, it's 100%. I just figured, you know, I could do it this other way, but I mean, this just doesn't make any sense. Yeah, no, it makes sense. I can respect that. Okay, any other ways we could have done this guy? My feeling then would be, even though I'm sure you didn't do it, so, and I don't necessarily care that much, but would be if you're going to implement it this way, in order for us to still have a fully functional environment, we would then need to come down here and apply env, And well, if we implement our has binding in terms of applying ENV, we only have to fix apply ENV, where we have an additional cond here that's looking for our extend ENV star, because our extend ENV star is now a list of variable names and a list of variable values. That make sense? Okay. So we'll circle back on that if it ends up becoming obvious that the book intended for us to do this rather than this. But both of them are fine. I mean, again, we're dealing with an interpreted language, so performance is not that important in the big scheme of things. All right, so let's look at the other question. Other question was the binary tree constructor-y stuff. 219. And then I'm going to look at some Lambda Calculus expressions and occurs free, occurs bound. We did look at the Lambda Calculus grammar last time. We just it was right at the end, right? So I didn't give you an assignment on that, but that's really where we're going with this next thing. Okay, so a binary tree with empty leaves and interior nodes labeled with integers could be represented like this. So an empty binary tree is that, or it's a tree that has an integer. It's a list of containing an integer in the car, and then a bin tree and a bin tree. In this implementation, implement the procedure number to bin tree. Okay, let's write that guy first. Number, something like that. And this guy is going to take in a val, and we're going to produce a list containing val, empty list, empty list. That. Effectively, it's a, we have a single number. We're going to convert that number into a binary tree using the second definition, second production of our binary tree, which has a list containing a number, followed by, has to be two trees. Well, there's nothing in there but that number, so two empty trees by this production. Make sense for number the first function? All right, then we have, okay, so produces a binary tree consisting of a single node containing the number. Also implement current element. Define current element to be a lambda that's going to take in a bin tree, and what, that's going to give us the car of the bin tree, the element we're currently looking at. That's what it's asking for. So there's our element, car of that bin tree. What else does it want us to do? Move to left son, so that's going to return the binary tree that is the left son of the current binary tree. It's going to be a lambda, takes in a bin tree, and it's going to return the catter of the bin tree. The car of the cooter. So that's the left tree of this guy. And I'm assuming the next one's move to right son. Lambda, bin tree, CADDR, bin tree. At leaf. So at leaf means that we are looking at a binary tree obviously it's not the empty list, because that's the empty tree. So it's a binary tree that is not the empty list, but has a car that's a number. If it's not the empty list, we know the car is going to be a number. What we're really interested in is that the catter is the empty list, and the CADDR, the CADDR of the list is also the empty list. That is a number with a left and right tree that goes nowhere. Make sense? That's a leaf node. All right, so define at leaf to be a lambda that takes in a bin tree. And this guy should return a true or false, whether we're at a leaf or not. So let's go ahead and let's handle the simple case. So we're going to say if null bin tree, return false, not a leaf, right? Otherwise, I'm going to kick that down. Otherwise, we're going to ask a follow-up question. And we could have probably done this in a cond. In fact, let's do that, just to practice our cons. All right, so that's the first test case. Okay, if I'm still kicking, that means that I'm not dealing with a null bin tree, so I might still be dealing with a non-leaf though tree. So I want to look at the CADR and the CADDR of the tree. And if both of those are null, then we're going to return true. So and null CADR bin tree, CADDR bin tree. If both of those guys are null, then we are dealing with that. And there's a shorter way we could write this, but let's just be explicit. Else, false. Not at a leaf. Make sense? We could have just written an else here and returned the and of all these things. That would give us the same answer, right? This says, if this is true, return true. Otherwise, return false. So we could have written that. Go ahead.
I believe it wants us to consider the empty list as a leaf with the way the question,
Wants the empty list to be a leaf?
with the way the stuff beneath it is written.
Oh, the examples? Okay. It sounded like the way they were asking. So we'll just change this to a true. We're good? Because it wants us to treat a list that is empty as a leaf node. Not sure that really fits a great definition of a binary tree, but it's fine. As long as we adhere to that definition, life goes on. Okay, that was at leaf. Okay, so now we need to do insert to left. I assume this guy's going to take in a... okay, so insert to right, insert to left, take in a number as well as a tree, right? This guy's going to be a lambda, val, and bin tree. All right, and we want the bin tree that we're taking in. Let's see, how much error checking do we need to do here? Is the presumption that this binary tree doesn't, that it currently has an empty list as its left child, or do we have to check to see what its left child looks like? Do the examples give us a hint of that? Huh? Okay. So the assumption is here's a real binary tree. It could even be the empty list, right? And if it's the empty list, I assume we would just make this tree the tree containing val empty list, empty list. I'm not sure was it explicit about that. Kind of a reasonable assumption, probably. So cond, and we'll go ahead and check null bin tree. So if our bin tree was the empty list, then we're going to go ahead and return a list containing val empty list, empty list. I think that's a reasonable approach to, if you tell me to add a something to the left of the empty list, you got to make your first node. All right. Otherwise, we're not dealing with the empty list, so we need to. The only guy we're interested in here, we don't really care what the CA DDR is, because that's the right child, but we care about the current state of the left child. Okay, so if the left child, so if null CADR bin tree, because we know it's that production of binary tree, if it's not the empty list, then it must be the production that has a number followed by a list followed by a list. So we can get the CADR of that. If that guy is the empty list, then we want to go ahead and return a list containing the car of bin tree, then containing a new list. That is our brand new node, which is going to be our val followed by empty list, empty list. That's our new left subtree. And this guy should be a list. Like that. So that's our new left subtree. If our left subtree used to be an empty list, we'll now replace it with a list containing our val and two empty lists. And then the right subtree will be whatever it used to be. We're not touching that. Right? So that's what we do if the left subtree is currently the empty list. Otherwise, left subtree must not be the empty list. It's a legit list, so we want to actually add our new val to the left of the left subtree. Correct? So else, we're going to go ahead and return the list containing the car of our bin tree, so whatever value is currently there, along with the result of insert to left of the val that we are supposed to be inserting, along with the catter of our bin tree, because that's the new bin tree that we're inserting that guy into. So let him deal with it, right? Onto the CADDR of bin tree. Oh, I didn't spell tree quite right here. I was testing you, Annie, and you failed.
I'm behind today.
What's up?
I'm behind today.
You're behind today? All right, so if we're in the else here, that means the left subtree is an actual tree with stuff in it. Therefore, we'll go ahead and replace that left subtree with whatever is returned by insert to left val and the current left subtree, which is a binary tree. So we'll let this function handle that. That look good? And then insert to right, I assume, is the other one. This guy is going to be a lambda, takes in a val, takes in a bin tree, going to be pretty similar to what we just did. Cond, if we're looking at null bin tree, go ahead and return a list containing val and two empty trees. Otherwise, we care about the right subtree being null. So else if null, CADDR bin tree, then go ahead and create a list containing the car of bin tree, the CADR of bin tree, and then a new list containing our val and 2 empty lists. Else, create a list of car bin tree, CADR bin tree, so just keep the left subtree alone, and then insert to right val and CADDR bin tree. That look good? All right, so go ahead and test these. Make sure this thing runs to begin with. Question and an answer. No. Oh, I missed a little parenthesis there. There we go. Number 2 bin tree. Oh, I had a capital T in mind. So list 13, empty list, empty list. All right, then we'll do, just for the sake of sanity, let's change our number to bin tree. Keep it a lowercase t. All right. Did it really need to highlight all of that? That doesn't make any sense, does it? Macintosh computers. Some garbage. All right, let's. Oh, it even copied it backwards. Okay, so these things go away, and it should look like that. Define T1 to be an insert to right 14 onto the insert to left 12 onto the number to bin tree of 13. List 13, list 12, list 14. Looks good. Move to left T1. What did I call it?
Move to left sun.
Oh. Isn't that what they told us to write?
Yeah.
Their example isn't even accurate? It's garbage.
Also, in the insert to left 15 and then T1, it wants you to put the 15 before the 12, not underneath the 12. Yeah. So be list 13, list 15 with the list 12, and then empty list.
Where's the one you're talking about? This last one?
Yeah.
Insert to left. Oh. So it wants you to make it the top level node to the left and then reinsert the guys beneath it. Okay. Rather than, because what we've done right now is we've had a trickle effect, right? We've said, go ahead and do this there. So instead, what we're going to do, does it just randomly insert? Like, does it do any checking for binary tree rules? Or does it just say, look, you want it to the left, it's to the left?
Like even there, that
Oh, yeah.
stupid, right?
It is stupid. I almost think our implementation is actually better. But I guess whatever. Okay, so they want that guy to be, so that's this one. And so, well, insert to left and insert to right, correct? So if we're in this one, rather than calling insert to left right away, we need to create a list containing our, well, now we need to look at the nature of the left node. Which kind of version of left node is it? If the left node is the, well, we already handled the empty list. This says, is the left node the empty list? So we know the left node has stuff in it. Actually, this had an error in it anyways. We didn't close that parenthesis there. This needed to be self-contained. But we're changing it anyways. So this should be a list containing our val. And do we automatically, because we need a right subtree there. So insert 15 to the left of T1. This is T1. So that should be 15 with the 12 and okay, so is the second element of it always going to be the empty list? That's dumb. That doesn't make any sense. All right, so then it's going to be list of val with the left list of that guy being the CADR bin tree and the right list being the empty list. Well, that's not even worth writing. And then this one will be the list containing val, followed by the empty list, followed by the CADDR of bin tree. All right, well, whatever. So I guess if you wrote something in the ballpark of any of that, that's good enough. Still practice with cons and stuff. All right, questions about any of that ish? Okay, so let's look at Lambda Calculus quickly so that we can give our first assignment dealing with that. All right, so this is going to be the grammar we're going to be looking at for the next several days. So we have a Lambda Calculus expression that can either just be an identifier, so that's like a variable name, right? Or it can be a list containing the word lambda followed by, so a lambda is an unnamed function, right? So it can be a lambda that takes in a list containing exactly one parameter. Can't be 0, can't be 2, it's exactly 1 parameter in our current grammar here for this guy. followed by a lambda calculus expression, where lambda calculus expression is any of these productions. Or it can be this guy later on we're going to call an app expression, because the first lambda calculus expression, this is a list containing 2 lambda calculus expressions. But the first one is probably going to be a function that we are then applying to this input. Does that make sense? This is an operand operator thing here. Okay, so those are our 3 productions. Then we're going to start adding to that, so we can, here, they call it an app expression right there. So the first one's a var expression, then a lambda expression, then an app expression. These would be our predicates for those. So now what I want us to write for Wednesday is, let's go ahead and write these 3 predicates, whether something is a var expression, whether something is a lambda expression, whether something is an app expression, so we can correctly identify those things. That makes sense? That should be, I would think, a pretty easy assignment. On top of that, let's go ahead and create getters for operand and operator. So the operand will take a lambda calculus expression that is an app expression and return the operand of it. That is this dude. We also want a getter for what do we call it? Observers. Is that what they called it in the book? Observers. So then we also want an observer to get the operator. Oh, I'm sorry, other way around. This would be the operand. So this is the operator, this is the operand. So observers for those 2 things. So 5 total functions. Our 3 predicates, var expression, lambda expression, app expression, and then 2 observers for the operator and the operand. Make sense? And I'll add that right now so I don't forget. All right, questions, comments, concerns, bribes. All right, and this should use that A-list type of implementation, even though we're not using environments yet. I don't like the data type stuff that the book has in it, so avoid the data type. Keep writing stuff the way we've been writing it in class. Okay? Lists of things is what I'm referencing.